Next up, we have Monica DeLay from Cytek Biosciences. And the talk title is Breaking the Fluorescence Barrier, Our Journey to 35 Colors and Beyond. Thank you, Monica.
Oh, and Monica, we just can't hear you just yet, but we can see your slides. Sorry, everyone, we're just having a tiny bit of a technical difficulty here. We'll just get everything squared away very quickly. And as a reminder, as Monica's getting her her audio squared away, just a reminder to everyone that we have our new Twitter handle at MetroFlowCyto that you can visit for any upcoming news and educational endeavors and all of that. So we encourage everyone to visit there.
Can you hear me now?
Yes, perfect.
Okay. I'm not sure what I did. I disconnected it and reconnected it. So
we're all good now. That's what matters.
Great. Thank you. Thanks for the introduction. And I'm very pleased to be sharing our updates and our journey to high dimensional panels with the Cytek Aurora. So as Christina and Catherine said, I'm Monica DeLay. I'm the US Manager for Applications for Cytek Biosciences, and I'm happy to be speaking with everyone today. So I'm going to go through our journey of how we got where we are now and talk about the development of the instrument and how we've been able to push beyond the 30 parameter barrier. So our journey began in 2017 when we launched the Cytek Aurora, which is a spectral cytometer for those of you who are not familiar with it. And over that next year, we really needed to start to characterize the instrument and understand how we could use fluorophores together to achieve not only adding more colors per laser, but really achieving high dimensional and high quality data with only 3 lasers. So I'm going to talk a little bit about that in this first portion of the presentation. So this is a optical layout of our 3 laser system. You can see we have a violet, a blue, and a red laser, and each of those individual lasers have a dedicated detector module. We use APDs, which is different from PMTs, but these are APD arrays, and each of those arrays has corresponding channels, and each of those channels is detecting a separate wavelength. And so what we can see here is this is our violet APD array, and we're capturing the emissions of every single fluorophore just past the laser wavelength and into the near infrared. So this constitutes a 38 channel instrument with just 3 lasers. So we take those, the emissions off of each of those arrays, and we can gather information about each of the fluorophores. And so this is just one fluorophore emitting off of all of the different channels. And what we're looking at here is essentially, you can think of it as 38 histograms on their side with the density shown. And when we stitch this information together, we come up with what we call full spectrum signatures. We always orient with the lowest wavelength laser on the left and increasing wavelength to the right, with also our emissions starting with the lowest wavelength emissions to the left, increasing to the right. So what we're going to talk about a little bit is what these full spectrum signatures are telling us. But first, before we started to explore these signatures, we really need to characterize the instrument and optimize the instrument setup. So the Cytek detection system is engineered to have low noise, to have exceptional sensitivity, and also we rely on the fact that each of our individual detectors behaves in a linear fashion. What do I mean by that? If I am to run samples, in this case, I'm showing some 6-peak beads, and I double my gain that I'm using, I should have a corresponding doubling in my MFI. So there's a linear relationship between the gain and the MFI, and we can use that. We actually do use that for some of the functionality in our software. So the next thing we needed to do was to come up with, because 38 channels is pretty daunting to optimize on an individual assay basis. So we wanted to come up with a starting point that people could walk up to the instrument and just start running. You adjust forward and side scatter, and then as long as everything's on scale, you don't have to touch any of the 38 channels. So we call this Cytek assay settings, and we base these on the performance of biological samples. Specifically, we wanted to make sure that we were getting optimal resolution of cells stained with anti-human CD4. So essentially doing a gain titration and allowing us to look at the resolution of different fluorophores across a wide range of gains. And because we have low noise and exceptional sensitivity, we have a very wide range of gains where we get optimal resolution. We also wanted to provide sufficient range to accommodate as many bright signals as possible. So if you've properly titrated your reagents, that you are minimizing the chance that something's going to be falling off scale. And finally, we wanted to preserve the spectral characteristics of each of the dyes that we were looking at. So we did not want to be changing the gains or having settings that would skew the native signature of each of the fluorophores. So we wanted them to appear as they should. And then the way that daily QC works is it takes these settings and adjusts them from day to day based on the instrument performance. So it really allows us to standardize the way that the instrument is set up from day to day. So once we have these optimal settings, we really wanted to explore signatures of different fluorophores to start to understand what we were seeing, understand what these full spectrum signatures were telling us. So a couple of things I want to point out for those of you that have not looked at these, not really understood maybe fully what we're seeing here. One of the things that was surprising is how efficient PE and PE tandems are excited by the violet laser. And so I think we all know that based on compensation in a conventional cytometer, where emissions are, but just being able to see that fully was very surprising. The other thing that is nice to see about full spectrum signatures, it gives us so much more information, and we can really understand which dyes are native, which dyes are tandems. For example, if we look at the signature for BB421, very flat across the first 3 channels of the violet laser, and we can tell which other BV dyes are also tandems of BB421 based on that signature. 2 other important things to mention, that in order to effectively use different fluorophores in combination in a panel, we require, or spectral cytometry requires, that the signatures have to be unique. If they are not unique enough, they will not yield good data. And then also we use spectral unmixing to deconvolute the signatures. There was just recently a webinar that FCS Express gave where Dave Novo talked about spectral unmixing. So if you did not catch that, I would look that up. You can get more information about how that works through that webinar. So now we understood what these full spectrum signatures were telling us. We needed to now characterize how they performed on the instrument and understand how they work together. What we did is stain cells with CD4 in many different fluorochromes, and then we calculated the reduction in the stain index due to spread. The calculation that we use is called a cross stain index. If you want to read more about that, we have a white paper on a resources page. You're welcome to check that out. For those of you that are Aurora users, you might not recognize this spread matrix. This was kind of an early version of how we wanted to visualize things. We've evolved even in that, and you'll see some of our more modern spread matrix visualizations later in the talk. But what we're looking at here is kind of just a rough characterization of low, medium, and high reduction in resolution from the fluors in the row to the fluors in the column. So a colleague of mine likes to call these perpetrators and victims. So these are the victim fluorophores where the resolution is reduced by these fluors. So using all of this information and using established best practices in panel design, we were able to build a 20-color panel. We were excited about this because we could use 8 colors off of the blue laser and then 9 colors off of the violet laser, which at that time was not possible with conventional cytometry. We were really able to kind of push the limits of a 3-laser system, which was very exciting. One of the things that's always been very important to us is maintaining high quality data. And so using best panel design best practices allowed us to do that. And I'm sure many of you have seen this data before. It used to be on our website, but this is our original 20-color panel. Again, good resolution across all the different markers. I'm going to point out a couple of populations because then we'll look at those as we go through the talk as well. So Tregs are here. You can see very good resolution of Tregs. And then NK cells, so I'm pointing out CD25 and then also CD56 here, resolution of NKs and CD56 resolution here. So kind of memorize that and we'll look at those markers again. CD56 is an APC in this panel and CD25 is in BB650 in this panel. So the next step was to see how many colors we could use effectively together while maintaining resolution. We didn't want to compromise the data at all, just by saying we could add more colors. But we were able to add some more highly overlapping dyes. So we went to 9 colors off the blue laser, 11 colors off the violet. You can see that we do have some highly overlapping dyes here. In addition to the ones we had before, but I'll point those out. So BB515, Alexa Fluor 48, PerCP Cy55, and PerCP eFluor 710. There's a few violet dyes that are very highly overlapping. And then also being able to go beyond 3 colors off the red laser is very exciting. So APC and Alexa Fluor 647. And then if we add a viability stain, such as Zombie NIR, which has a unique signature from any of the other dyes off the red laser, we're able to push that to 5 colors off of the red laser. And again, looking at the data, so this data is on our website. So again, maintaining that resolution was very important to us. Let's point out the Tregs. So again, memorize, I hope you memorized the resolution, CD25 and PE. And then here's our CD56 in BB711 this time. And again, maintaining that resolution it was done. We were successful. So the next stage in the development of the Aurora was to add more lasers. This really pushed the Aurora into what we would consider the high-end cytometer category. We started, obviously with 3 lasers, and now when you have a 5-laser system, it can really match what is being considered a high-end cytometer in the conventional world. So adding more lasers really expands the possibilities. One of the things I want to point out is the signature of PerCP and PE-Sci5. So we, again, starting from a 3-laser 38-channel instrument, these two dyes peak in the same channel. Even though their signatures are slightly different, maybe they're unique enough to use together, but they're peaking in the same channel. It's not really ideal for panel design. But when we expanded to a 5-laser system, 64 channels, now these two dyes peak in separate channels, and we're more able to distinguish them because their signatures are much more unique. We're taking more measurements across all of these different channels, going from 38 to 64, and also adding the capability of the yellow-green excitation. So adding these lasers did require us to kind of recharacterize the system. We needed to understand what new dyes we could add, how these dyes were going to perform together, what happens when we add these new lasers, how does it affect our panel design. So this is just one of the comparisons that we've done. So 4-laser system with the UV, so this is UV, violet, blue, and red, so without the yellow-green, versus a 5-laser system with the yellow-green. As we know, yellow-green lasers excite PE and PE tandems much more efficiently. With that more efficient excitation does come a cost. We do get more spread. I'm just pointing out one section here on each of these spread matrices, and you can see that our spread matrix now looks different. We've colored it a little bit differently. But this is just, it gives us information, right? So this is something that we have to consider when we start to think about our panel design. So not bad necessarily, it's just more information. So again, adding more lasers and more channels really expands our possibilities. We're able to separate a lot of these blue dyes off of so that we can put our PE and PE tandems over in the yellow-green. We're able to add a whole bunch of new UV dyes to our panels, and it really took us from being limited to kind of 24 to 25 colors on the 3-laser system to being able to expand beyond 30 colors. So that's what we're going to focus on the next section of the webinar. So like I said before, when we added these 2 extra lasers, it launched the Aurora into the, or pushed it into the high-end cytometer category. So this was the first time we were able to really have a direct comparison with a conventional cytometer. So we chose a panel of 21 colors that we knew worked well on the conventional cytometer and compared it to the performance of the Aurora. And we used the same controls. So the samples were prepared, split in 2. The controls and the 21 color sample were acquired on both systems simultaneously. The first thing we wanted to do was to take those controls, run them, and then do calculate a spillover spreading matrix. So some people might be more familiar with this calculation. You can do this in FlowJo. And you can see when we compare our controls, we have much more spread, so higher values on the conventional cytometer. We're taking more measurements and we're gathering much more information on the Aurora, plus we're using spectral unmixing. This gives us much more power, and our spread matrix is reduced. So now with the data comparison, we can really see those differences in the data. So I'll just point to some areas here where you can see some increased spread in the data on the conventional cytometer versus the Aurora. And again, this is identically scaled multicolor data, so we did not do any tricks with the scaling. So once we started really understanding how the 5-laser system worked, we wanted to start to add more dyes, but we really needed to understand how these dyes work together. So we started to build some more panel design tools to allow us to push beyond the 30 parameter limit. So I'm just going to kind of go through a quick overview of the different tools that we have available to our users. We have our Fluorochrome selection guides, which give us a bunch of information. They're configuration specific. So unique dyes, it gives the stain index, the spread matrix, recommended dyes that you can use in combination. We also have our spectrum viewer that we launched last year, which has been very handy to be able to look at normalized signatures and compare different dyes together. You can also build kind of a theoretical panel and look to see how spread out your peak emissions are. Obviously, we want things to be more spread out across that full spectrum versus clustered together. And then we developed some metrics. So it was very helpful to understand how similar or different two dyes were. And then using a combination of dyes, how we can kind of assess whether that combination of dyes is going to be a good idea or a bad idea. So we developed the Similarity and Complexity Index. So again, those Fluorochrome selection guides we have, because it's going back to the way that we standardize the instrument setup, so we know how these dyes can perform using those Cytek assay settings, and we're able to give our users that information. It allows you to, we kind of do the hard work for you so that you can be much more informed when you start to build your panels. So this is an array of fluors that we're showing the different stain indices from lowest to or dimmest to brightest. And then this is a spread matrix for a 30 parameter or 30 fluor combination. So we can, again, use this information to start building our panels. So again, to try to push beyond that 30 color limit, we needed to understand how to measure dye pair uniqueness. So the more unique dyes are from each other, the easier they're going to be used. We're going to be able to use them together in a panel. So we came up with a metric, like I said, so it compares these two spectra to each other. So in this case, we have PerCP eFluor 710 and PerCP Sci55. You can see they are very similar, but they peak in separate channels. So index of 1 is identical, and an index of 0 is that they're completely unique. So PerCP eFluor 710 and PerCP Sci55, we have a similarity index of 0.9. If we compare another pair of dyes, BUV 395 and APC, our similarity index is 0. So it gives us a, kind of a range, or to be able to understand how similar or different two dyes are, and allows us to start to think about picking new dyes that we can implement in our panels. And what we found is that a similarity index of 0.98 and below are usually okay to use in a panel, as long as you're taking into a consideration best practices in panel design. So the complexity index is a little bit different. The complexity index is a combined index, meaning if I take a combination of dyes, whether it be 2 or more dyes, 10 dyes, 35 dyes, I can understand what how complex that combination of dyes might be, how difficult it will be for me to design the panel. So it's an overall measure of uniqueness of all of the dyes used in the panel. So the lower the complexity index, obviously the easier that combination of dyes is going to be to work together. And it's really useful for helping us to pluck in more dyes where we have gaps in the spectral signatures. So an example of some complexity index values is the 10 dyes at the left. The complexity index is 2.5, and our 35 color panel that we're going to be talking about in a second is 46.4. So we're kind of in a new era of flow cytometry where we're no longer limited by hardware. We're kind of limited by fluor selection. And so finding new unique dyes that we can put into our panels is something that we're exploring right now. We are also developing some new dyes. So cFluor 568 is one of those new dyes that we've been using. And you can see that it's very similar to PE. However, there are some differences, and the similarity index is 0.88, which is much less than that 0.98 kind of cutoff that we have for our getting good data. And we have used this in our panel. So this is an example of using cFluor 568 on CD4 and using CD25 and PE, which are these two dyes, which are very similar, but you can see that we still get very good resolution. It's not impacting, the CD4 is not impacting the resolution of the CD25. So working very well together. So taking all of that information we've learned about characterizing the instrument, understanding how fluorophores work together, now we have these new tools. We can start to explore which fluorophores we can start to add to our panels. And we even evolved in the way that we look at our panel design. So what I'm showing here is a panel grid that allows us to very quickly assess the quality of our panel design. So we've labeled our different markers, primary, secondary, and tertiary. If you want more information about best practices in panel design, this is an excellent resource. So this gives us an idea of balancing antigen density and fluor brightness. We can also look at co-expression in this regard because when we organize our fluors this way, we can understand where we're going to anticipate any overlap or spreading error from certain dyes into certain other ones. For example, if I look at just the violet laser and I know that these three dyes overlap quite a bit, I also know that I'm going to have some spread. So I want to be careful about how I assign my markers to these fluors. In the same token, if I look across the lasers in the same emission area, this is usually where I'm going to have overlap and also spread. So I can very quickly see, do I have markers that are co-expressed or do I have my co-expressed markers spread out so I can minimize that impact to the resolution.
Monica, just to let you know, we have a little less than 4 minutes left.
Great, thank you. So here's the 35 color data. Again, I'm going to point out T-regs so you can see we have very good resolution even with 35 colors. And using that very high quality, good resolution data, we can use high dimensional analysis techniques. This was a very interesting finding. We used 3 donors for this 35 color panel. And donor 1 had a population that was identified that was not present in the other donors. And we were able to really explore that population using these high dimensional methods. And then using those same concepts, we were able to push to 40 colors. So we had a press release in September of 2019 where we hit our 40 color achievement. And if you want to know more about that, you're welcome to request a poster at cytekbio.com. And we will be sharing this information soon. We do have a manuscript in preparation. We'll be excited to share all of the information on our development of the 40 color panel with you in that regard. So now it's 2020, the journey continues. I just want to share a couple of things about exploring new dyes and what's coming up from Cytek. So we have, remember we use APDs in our detection system, which have an excellent quantum efficiency in the red region. So finding new dyes that emit in the red region is one way for us to add new dyes to our panels. So here's an example of APC Fire 750, and there's a dye that we've been using in one of our 36 color panels that we've been working with for collaborating with COVID studies. And you can see that they peak in separate channels, and this is some data showing them being used together. CD38 is in APC Fire 810, and HLA-DR is in APC Fire 750. And then finally, this year, look for some updates from Cytek. We have some new dyes coming out. So the cFluor 568 is just the first in a line of new reagents. We have more to come. And then I also am very pleased to tell you that this year we'll be launching a new version of SpectroFlow, SpectroFlow 3.0. This is our software that runs our system. We will be implementing CFR Part 11 compliance, improved workflow for just going through the experimental workflow, and then we'll have some enhanced worksheet functionality as well. And with that, I'm more than happy to take any questions that people might have.
Thank you so much, Monica. As usual, that was absolutely wonderful. We have 30 seconds, so let's see if we could speed through one or two questions.
No problem.
So Kurt Van Gunst asked if there was a way to turn off the 561 nanometer laser on the 5 laser system to reduce spread.
So let's talk about that offline, so we can talk about what your needs are. I mean, not by default. We do have some users that we've discussed this with. So yeah, we can talk. Yeah, feel free to contact me. My email is mdelay@cytekbio.com.
Okay, great. And we do have one or two other questions. We'll explore a way to answer those after the fact for today. So we'll make sure that we get those questions answered.
No problem.
And we have, and thank you again so much, Monica. That was great.
Thank you. Appreciate it.